screen here. There we go. I think that's working. So first,
Yes.
let me say it's great to see so many people online. The workshop in 2016 was cozy and really nice and get to know everyone. But I'm hopeful this is indicative of an expanding field and more work in optical SETI. So there we go, advancing the slides. I'm going to go really quickly through what is LaserSETI, why is it designed the way it is, and how does it work. And hopefully we'll have time for questions at the end. So as Paul showed, LaserSETI is a camera system. It's a little awkward to talk about because there's two cameras in one instrument, because one camera is rotated 90 degrees from the other. It's a simple optical system with a very specialized transmission grating in front of two off-the-shelf components of a lens and a camera. The other special thing we do, as Paul described quite nicely, is the TDI overdrive. We clock out at just under a millisecond, and it, as I'll explain later, has some unique and cool effects. Thanks to this very special past year, I still have the instruments waiting to go to Hawaii. So again, as Paul showed, and you can see a little bit more closely in the bottom right, what the instrument looks like with the two cameras. And actually, let me back up. Just wanted to describe a little bit more in that if you look at the purple thing, that's a Raspberry Pi, which is kind of the central nervous system that controls the sunshade, has the GPS that's accurate, gives us a time signal that's accurate to about to within a couple microseconds. The cyan box you can kind of see hidden underneath the nearer camera is an i7 PC, and that's really the brain that does the real-time data reduction, analyzing the quarter gigabit of data that comes off the two cameras in real time. And then the green box underneath it is a hard drive that we use for storing as a circular buffer to store the raw observational data, as well as anything we thought was interesting and worth saving. So the instrument is pretty, is very self-contained and meant to be robust and automated. So where we are is currently in the Ferguson Observatory. We're on top of the Ferguson Observatory. They have a great facility here in Sonoma, California. Those two are actually, this picture was taken before they were painted, the covers were painted white for thermal. As Paul correctly reasoned, the boxes get hot in the sun. And you can see in the inset there is the all-sky camera for the NASA partnership that I'll talk about a little bit later. Phase 2 was about building the first two sets of instruments, two looking west from California and two looking east from Hawaii. Again, thanks to the very special past year we've had, we're not there yet, but you can see where we're going to sit on top of the Airglow building. We're looking in the picture on the right at Pan-STARRS 1 and 2. And don't tell Pete that we're at a higher elevation site than the Air Force telescope on Haleakala. Oh, and actually the other thing I wanted to mention on the slide was due to more than just COVID last year, even though we haven't quite finished phase 2, we're moving on into phase 3, where we're adding 3 more observatories in the Eastern Atlantic, Caribbean, and South America. And as is very important for SETI, we're already more than halfway funded for that. We bought the hardware and we're really making good progress towards expanding the network from the original. Phase 2 was just make sure the dang thing works. And phase 3 is let's expand this thing out and get some real science done. So a couple of things make LaserSETI particularly unique. One, since many SETI projects start from the hardware that's on hand or what can be done, and then see if we can get the funding for it. we decided from day one to design for a reasonable funding envelope. As they say in the right stuff, no bucks, no Buck Rogers. And so this has guided a lot of the decisions we've made, in that the goal is actually to get to the end of the project, build all of the instruments, and my theory is that we'll get more science done by having reasonable funding expectations. We'll see if the theory proves correct or not. We were early on in the all sky all the time. That just seemed like the thing to do in terms of covering more uncovered parameter space. But one of the things I want to mention is that when you're looking at all the sky all the time, you have an opportunity to spot many more transients than if you're looking at a small section of the time for a small period of time. And so that I view that as a direct correlation, that when the wider your field of view, the higher the need for your ability to have high confidence in what you detect, because you have a much greater chance of finding something that you're not going to be able to go back and look at later. And I'm glad Paul is here. I sometimes quote Paul for what I think he said at Breakthrough Discuss. I think it was the first Discuss, when he said, "My least favorite SETI result is a bunch of maybes." And so I don't know whether he disputes that or not, but I could swear he did say it. We'll have to go to the videotape maybe and see.
I confirm that.
Okay, excellent. I thought we'd discussed it one time, and I thought you didn't. So that's great to hear. I'm not crazy. So anyway, LaserSETI was designed explicitly from the beginning to have a extremely low false positive rate so that we could have extremely high confidence. I believe the number we actually calculated out was a false positive in 10,000 years if we were running all 60 systems, all 60 instruments globally. And that's obviously processing a huge amount of data. The last thing I thought was interesting about LaserSETI and the principles is that we're able to, if you look at the readout cadence on the CCD, it's that 900 microseconds. But our transmission grading allows us to integrate far above the readout cadence and detect signals that, that square wave or sine wave could be, many seconds, even minutes long, and we can still integrate on that time scale because we have the spectral discriminant. And so I tried to create this graphic last night that I thought was interesting to think about optical SETI, and I was really excited to hear what we're doing with TESS, because traditional supernova and near-Earth object observatories like Atlas and Pan-STARRS and Catalina and them, they're not looking for transients, they're throwing away things like this. And I'm excited to hear what we're going to do with LSST as well, because I think there's a really interesting section of the time domain here, as well as, of course, Vasco I'm really curious how that's going to pan out. But LaserSETI, because of this spectral area, can cover a huge amount of range of signals. And as the Benford family has eloquently shown, there are some really interesting signals to be detected on this timescale. And so I think we should be looking at optical SETI with this lens, and I'd be really interested to help flesh out this diagram. Just to give a brief grading of what LaserSETI is good at, it's really good at finding something that's bright and transient. It's not good at the other kinds of interception, not because of its properties, but actually because those are just really hard to detect because the signals are too weak and the beams are too narrow. It's really good at detecting an intentional signal, although its sensitivity is obviously not as good as larger apertures. Doing things like a solar gravitational lens, natural lasers, well, semi-natural lasers, I should say, are interesting, but I grade us lower because I've not seen anyone talk about lasing within the optical. I grade us, since we don't know anything about a SETI signal, I grade us okay at the unknown, in the sense that since we cover a huge amount of sky and a huge amount of the time domain, we're pretty good at detecting an arbitrary signal within that parameter space. And then on the non-SETI science, things that burn up in the atmosphere, because we have a wide field of view, a high time resolution, much greater than the 30 frames per second from that most people are using best case for their all-sky cameras, and the spectral capability, we're pretty interesting for being able to analyze things that burn up in the atmosphere. Oh, and the acronym stands for Asteroid Threat Assessment Program, where they're trying to understand how, if you know where something's going to hit the top of the atmosphere, how do we know how it's going to burn up and evolve and end up potentially hitting stuff on the ground? So the first how we get things done at LaserSETI is we have a team of incredible people, and I didn't want to get to the end without mentioning them, although I won't read you the names. So one aspect of cost is those commercial off-the-shelf components. We're using a camera that was chosen because of its wide field of view, high quantum efficiency, and high TDI shift rate. We're using the lens because of its large aperture. We get a pretty decent spatial resolution out of that. To spend just a little bit of time in case Paul's whirlwind explanation of TDI, which frankly I think is really good, but I think I have never seen anyone wrap their head around this observation technique in less than 10 minutes, so I figured it would still be worth going through this. The transmission grading takes a point source and spreads it, a broadband point source, and spreads it into two spectra. You have the zero order in the center, and the grading is optimized to concentrate into the plus and minus 1. So you see the hotter star is concentrated in the blue on the interior, the cooler stars in the red in the exterior, and a laser pulse would either be 2 or 3 dots. So our transmission grading nulls out the zero order at 540 nanometers. So a green laser will show up as 2 pure dots versus a blue or a red laser will be 3 dots. And so that's an extra component of the signal analysis that not only is the spacing a function of the wavelength, but so is the ratio of the brightness from the first orders to the zero order. Again, just to help people wrap their heads around it, this is what it looks like to look out the instrument with the full frame registration frames that we build. You see clouds and they look kind of ghostly. All the stars have the zero and first order. If you looked quickly, there is an airplane flying through. But then the way we only take registration frames every 15 minutes for 10 seconds. The rest of the time we spend with the shutter open doing this crazy TDI thing. And so I thought it was good to show just the real data of what it looks like to see a signal. You can see the zero orders here right in the center, and then the lobes on either side. And so these pulses are spread out not very much in time. You can see it is actually more than one row vertically, but you can see what the algorithm is looking for in the TDI data. The last element of how is this commensal observing strategy that Paul brought up in the beginning. And so we've gone with sites that are over 1,000 miles apart. And so that not only when we co-observe a field of view, you can see all these parallel lines that represent the direction of view from each instrument. So every site is designed to observe with its neighboring sites and match those fields of view. And so of course we get the increased statistical confidence. Instead of 4 spectra coming from 2 cameras and 1 instrument, if we observe an event, hopefully we get 8 spectra coming from 2 instruments. But since we have this super accurate clock coming from the Raspberry Pi, we can actually measure the propagation time difference as an additional physical validation. Also, against spoofing, the pixel resolution with this baseline means that we can spatially discriminate a source within about 25 times the Earth-Moon distance. And so it'd be pretty hard for Haddon Enterprises to put something in low Earth orbit and fool us. And lastly, of course, since no site has perfect weather, it's just good to have 2 sites, because that way even if you don't get both your instruments on the event, you might get one, and maybe that's a confirmation that happens, and you saw, you know, if it's something that repeats every 3 months, and you're able to catch it sometimes with one and sometimes with two, or maybe you just catch it at all and you don't have as quite high confidence. But when you're trying to get all sky all the time, it's also worth thinking about how do you really get all the time. That was what I had, and I hopefully have time for questions.
Thanks. So yeah, we do have time for questions. So I see David. Just raise your hand. Is that a question for Eliot? So here's a question from Cosmic Boost. What is your sensitivity to natural 10-second flashes?
I think the number I have in my head is about 1 photon per square millimeter. I think that's just approximate. I've been actually looking to refine that using the system actually analyzes the noise in real time when it's looking for signals above the noise. And I wanted to do more than just a theoretical calculation and see what the system is doing. I haven't had a chance to run that analysis, but it's on the order of hundreds of thousands of photons per square meter.